Right. Once again, welcome back, folks. This time around, we want to see if we can discuss about solutions to the 10 examples that I have. The first problem here is we want an explanation as to why assembly language is easier to write than machine code. Well, assembly language uses mnemonics, which are human readable as opposed to machine code, which uses binary. So what's our argument here? We are saying binary is just a set of zeros and ones, which sometimes are difficult for a human to process or remember. Then the next problem, we want a similarity between assembly and machine code. Here we are saying both these languages, they are machine dependent. No assembly language uses a two-pass procedure to come up with the bit formats, but I mean, in the end, the final product is simply sets of zeros and ones. And one other thing to note is assembly instruction usually corresponds directly to machine code instruction. So those two, they are also specific to particular processor architecture. So that's what we have on a similarity between assembly and machine code. Then next we want to look at a description of pass one of two-pass assembler. So the first step is we identify all labels. So identify all labels, all labels. Let's see, identify all labels. But one key thing to note here is no machine code is developed in the process. So we assign and store memory addresses. So assign and store memory addresses. So like I said, the key thing is no machine code produced yet. Used yet. So obviously, if we are going to look at pass two, it tells us that machine code is going to be generated, but there are some procedures or steps that will be followed before that happens. For instance, we're going to translate mnemonics into opcodes. So here we say we translate mnemonics into opcode. And the idea is to finally end up with the machine code itself. So before that, we replace all labels with their actual memory addresses. So replace opcodes or labels with memory addresses. And once that is done, then obviously we will have machine code being generated. So we will then generate machine code. Let's look at the fifth example. Identify the instruction type add register 1, register 2. So this is an arithmetic instruction. In other words, we are performing calculations such as add, multiplication, you name it. Then the next problem we want to look at, we want to explain immediate addressing with an example. Immediate addressing with an example. So we can have an example like load into register 1. So load register 1 and a number like 5. So here we are simply loading a value 5 into register 1. Then next we want to go through steps here. We want to try and load register 1 with number 4, then add into register 1 a number 3. So the solution here is going to be in register 1. We are going to have a result or a solution of 7. So if we do it step by step, we are saying when we load register 1 with a number 4, so register 1, it means it stores a number 4. When we add into register 1 a number 3, then it means in register 1 we'll be having a value of 7. So the final output we are saying in register 1, the value that is stored is actually a 7. Then we want to perform logical left shift on this number. So in other words, we are shifting each bit one step to the left. So if we check there, it means we have 2 zeros, then 1, 0, 1, 1, 0. Now, because we shifted 1, there's nothing there, we put a 0. So that's logical left shift on that given byte. Then instead, the effect of logically shifting right by 1. So shifting right by 1 is as good as division by 2. So it's arithmetic division by 2. So when we are moving to the right, we are dividing by 2. When we are moving to the left, it means we are multiplying by 1. I mean by 2. So what we'll be having is a number half its initial value. Explain how AND can be used to check a bit. So when we do AND, we are trying to come up with more of a mask to test whether a bit is set or not. So AND operation is performed in this process and is used as a bit mask to check if a bit is set up or not. So the result of 0 override tells us that the bit is not set. The result of 1, it tells us it was set. So let's just have a look at a basic example to say how do we use bit mask. Let's say I've got a value. I can just think of a nibble to say a value like 0, 1, 0, 1, 0, 1, 0, 1. So I want to mask it with a nibble 0, 0, 1, 0. And the result of this masking is going to be a logical AND in corresponding bits. So if I do my AND, this is going to result in all points giving me zeros. So it means there is no bit that is set. So that's an example of bit masking that we perform to check if a bit is set or not. Thank you, folks.